Namaskar. Welcome to Prakash on Basics. I'm Prakash Zog. We've talked of lasers, and I'm coming to the last part of lasers today. This is going to be a little technical, a little of science and technology, a more difficult area. Um, but I felt that since we are talking of lasers, I couldn't skip this particular part. Uh, for non-science people, it could get a little more difficult than normal. I'm not going to deal with any equations or go into that part of details. Uh, I'll try and keep it as simple as possible. We are going to talk of the different types of lasers and how they work to some extent. Uh, we talked of all the applications, practically hundreds of them. Uh, it is quite obvious that at each point, the property that is used of the lasers could be slightly different. And so naturally, then the expectation from that particular laser could be different, in which case it is obvious that you would need different types of lasers. And it is these that I am going to talk of today. With a vast range of applications, the lasers need to be different. And this difference is based on quite a few different factors. The first obviously is what is the method by which they are produced. Then it deals with the amount of energy that is involved. The energy would vary right from milliwatts to gigawatts, where it is used to cut sheets of metals, etc. Um, it would also depend upon the range of the wavelengths that are produced by in the laser form. It could be in radio wave region, or in the infrared region, or it could be the visible lasers, or it could be UV lasers, and to the other extreme, which is the X-ray lasers also, which are in progress or of development. So that's another area that differentiates them. It also depends upon whether it's a continuous beam of laser light that comes out, or is it pulsed, and that pulses could be of very high frequency. It could also be something like a self-terminating type of a laser, like the nitrogen laser. The pulse laser could go into femto level, the optical use that we talked of, which is for your retina and its corrections. So these are some of the ones, but there is a major factor, and that is depending upon the type of material that is used to make the lasers. Um, I told you that the actual part that causes the laser action is known as the active medium. Also, it is placed in another medium or surrounding medium, and this could be in the different states of matter that we know of. It could be solids, liquids, gases. Actually, matter has two more states, plasma and Bose-Einstein condensate. But keeping that aside, those two of them aside, there are others also, like semiconductors, and then there is something known as excimer lasers, and then the most recent one, and rather the most complicated one, which is the fiber optic laser. So also it will depend upon the different type of energy levels that are available. The energy levels could be only two of them, in which you would have a monochromatic beam of laser light, or it could be multiple levels, or it could be 3 level or 4 level laser, and so forth. So these are the different types of categorizations of how lasers can be talked of. Um, let's not make it so much more complicated. Let's try and look at the physical state of the substance, and then identify how these lasers are produced. It's very interesting in some of the parts. Matter, as I told you, could be solid, liquid, gas, plasma, or it could be a Bose-Einstein condensate. And in all these, the first three are the ones in which lasers are a little more popular. The first obviously is the laser that we started off with, and its details of how it is produced is what I talked of, and that is known as the solid state laser. and then I just to remind you, it's a ruby rod which is doped with a certain ions of chromium 3, and it is these chromium ions that go up and down, and then population inversion, and that results into, as we said, the laser beam that is produced. And that of course was the first laser that was produced. But among the solid state lasers, the one that is commonly known nowadays has a short form name. It is known as a YAG laser. Yttrium aluminium garnet is the technical name of the material that is used, and inside it there are certain ions like chromium. Instead of chromium, in this case the ions are of Nd. Nd is neodymium. It's a rare earth element, and that is the one that transits up and down and results into the lasing action that we talked of. In this case, of course, like last time, there is a flash lamp that is around, and it is the flash that produces, and then the laser action starts off. It's a pretty compact type of a system, and it's quite robust, easy to use, and it has a lot of high output power. But the cost of all these solid state lasers is quite a bit. So they started trying to test out and find out if there were other methods of producing these laser beams. And the second one that was invented is the gas laser. Probably it is the most important type of laser that was put to practical or industrial use. Many of the applications that we talked of were actually based on gas lasers. It was first invented by an Iranian scientist. His name was Ali Jawan. That is around 1960. He was also working for what is known as the Bell Labs, and there this gas laser was invented, which worked in the infrared region. There itself in Bell Labs was invented, depending upon the type of the gas that is available. It could be either atom, or it could be a molecule, or it could be an ion, and so forth, or a more dimer or a more complex type of a molecule. The one that was developed immediately after the first one was the carbon dioxide molecule type of a laser. It was invented by an Indian American citizen there. His name was Chandrakumar Patel. This was around 1963-64 is the time when he invented this. Mr. Patel was Dr. Patel was originally from Baramati, studied in COEP in Pune, and instead of going in for IIS and other areas, he went into working for science. Went to the US, and one of his achievements was this great thing that he talked of, which is the CO2 laser. He was given a lot of awards in the US for this major invention that he had carried out. CO2 laser is slightly different from normal laser, but it's very interesting. So we must know a little more details, more because of the interest of how it works out. One thing is that it doesn't use a flash lamp to trigger on the population inversion or the rise of the electrons to higher levels, but it uses a discharge tube. A discharge tube is a low pressure tube to which voltage is applied, and that voltage causes the electrons to move around. We talked of this when we talked of tube lights, the Geissler discharge tube and so forth. So that's pretty simple, but a little more complicated manner in which it is made for these applications. So this now uses not light pumping but electrical pumping. And the final transitions or the jumps that the electrons make is associated with 2 levels, and so this CO2 laser produces 2 wavelengths, 9.6 micrometers and 10.6 micrometers. Let's look into some major ideas that are associated with this. First of all, it's a molecular laser. Molecular because CO2, 1 atom of carbon, 2 atoms of oxygen, they form a molecule, and it's a linear molecule. That means all of them are in one particular line. Very simple. Let's say it's my head, let's say, is the carbon atom, and I have 2 oxygen atoms. on either sides, and they are all in a straight line. Of course, the sizes are exactly opposite. Carbon is smaller and oxygen atoms are much bigger in size. Now, whenever anything is given energy, the major change is rise in temperature, of course, but the major change is in its kinetic energy. We will talk of this when we start talking of heat a little more detailed. But right now realize that it is the kinetic energy, and kinetic energy is nothing but a vibrational energy. So the molecule begins to vibrate in a number of ways. In fact, not only does the molecule vibrate, but the atoms themselves begin to vibrate around, and it is this that is typically referred to for lasers. It is referred to as the stretching modes of carbon dioxide. Think of what is going to happen. Carbon, oxygen atoms on either sides, and energy is given, electrical energy is given, and so it starts going into different stretching modes. The simplest form would be when the carbon remains stationary and the oxygen atoms move outwards and inwards, and this is one type of stretching motion. This is symmetric on both sides, so this is perfectly normal. There is another possibility that these two come closer, and then these two come closer, and then these two come closer, and then they start moving like this. So this is a non-symmetric or asymmetric vibration. There is another bending type also, in which the oxygen atoms go downwards and the carbon atom goes up, and then reverse. So they are moving parallel to each other, but they are moving in opposite direction, and that is also putting strain on the various forces that are there between the two of them. Why does this happen? It is obviously because of the electrical energy that has been supplied. It cannot remain. This is a typical, this asymmetric one is the one that is metastable. We talked of metastable. Metastable is which is not going to remain as it is, but that has resulted into more number of higher levels. So it's going to come down and produce the laser that we had talked of. So how do you go about this? So what you do is you take a tube, put not just carbon dioxide, but major part is helium, a bit of nitrogen, and a bit of carbon dioxide. Carbon dioxide and nitrogen are molecules are practically similar in number, 1:2 or 2:1 ratio, while roughly if that adds up to 3, then about 7 times more will be the helium atoms and helium molecules basically that will be present. So that's a mixture. In addition, sometimes hydrogen is added in small traces, sometimes water vapor is added in small traces, depending upon the requirement of the particular situation. So it's a mixture, and when all this energy is given, there are a number of levels of higher levels that are produced. It is only 2 of these levels where that 9.6 and 10.6 micrometer wavelength light in the infrared region is given out, and that results into moving between 2 parallel extremely polished mirrors, one partial, and then out comes the beam of CO2 laser in the IR region. That's how it works. I've just tried to recollect what we already talked of, but for a solid state laser. Now this is how it works, and then the beam is utilized wherever it is required. It can be either continuous or it can be pulsed. This was the, and its use, of course, because the wattage could be drastically different. It can be used for cutting very thick metals, vaporizing metals and slicing and so forth, applications of industry that we talked of last time. Simultaneously, around that same time, there was a second type of a gas laser that was developed, and this is known as the helium neon laser. It's obvious that it's a mixture of helium gas and neon gas, and it is the neon that keeps on undergoing transitions and produces the laser. These are the when they go into their ionic state. In fact, this is also around the same time, 60s, when it was in mid 60s when this was developed. In fact, the first laser that I had the privileged to see in Department of Physics around 1974-76 somewhere was this helium neon laser. So that is the first laser that even I did see. So that, and it had very small power, but it's very a box-like structure. It was pretty costly at that time, and even today it's not a very commonly used laser, but it was among the earlier lasers that was developed. It was replaced by quite a few other type of lasers that came forward. One more gas laser that was equally important was nowadays that is put to use is a nitrogen laser, and this nitrogen laser is the one that has only 3 energy levels, and so it's a pretty interesting simple type of a laser. And it has a speciality. It's a self-terminating laser. That means after a certain time it switches off. It has to wait for some time and then starts up again, and so forth. So that's a special type. It is also used quite common because it's pretty simple to build and so forth. So these are the gas lasers. Solids, gases. So obviously the third logical approach was to find out if liquids could be used for this, and that resulted into liquid lasers. But actually they are not called liquid lasers. The reason is pretty simple. What is added to it, which is obviously the active medium, is a different chemical, and these are known as dyes. Dyes are the materials that tend to give color to things. So that's what dyeing process, वगैरह, that the word that we have heard. These are known as dye lasers, and coumarin or rhodamine and phthalocyanine, these are the typical dyes that are used. They are dissolved in certain organic solvents like ethanol and acetone, and sometimes even water, and it is this mixture, this liquid with the dyes inside, that produces the lasing action, and because of various triggering processes that are used. So the active medium is really the dye. It has its own special property again, and that is these dye lasers are said to be tunable continuous output type of lasers. Tunable is like the radio that we talked of. When you change the dial and you can change the frequency, same way here also it is possible to change the frequency of the laser that comes out. And that's a big advantage, because you can do a lot of testing using this. So naturally these type of lasers are used in the area of study of light, which is typically known as spectroscopy, spectral analysis of light. It is also in photobiology. Photo is light, biology is applications in biology, obviously. So photobiologist is trying to study the effect of light on various objects, various types of lights and so forth. For that these tunable lasers are used. It is also used in medicine. So this is more of science and research area type of a laser that is talked of. 1, 2, 3. Now you come to the fourth one, which is the most commonly used laser nowadays, and that is the semiconducting lasers. We've talked of what semiconductors are and what diodes are and what LEDs are, say a few months back. This is something very similar, but there is one thing that I must point out very specifically. If you look at the variety of material that is available on lasers, and it is taught in engineering and other areas also. And what I have come across is they do not specify one major issue in this. They only say that it is a semiconducting laser, but they don't say that these are typically compound semiconductors. And when you talk of compound semiconductors, they are totally different. Let me just remind you, fourth group elements are the ones that produce semiconductors. Out of that, typically silicon and germanium. And they are doped with third group or fifth group. You forget the middle one and use directly the third and the fifth group and combine them. If you make more of this, you get N type. If you make more of this, you get P type. And that's how you get compound semiconductors. And all these new type of lasers that are put to use nowadays are for lasers specifically are compound semiconductors. So please keep that. That's something that we must know. It's not normal semiconductor that we are talking about. Which ones are used then? Obviously something from the third group and the fifth group. And what is so special about it? Their energy difference is such that when the electron jumps down, the light given out is in the visible region. That means you can see it clearly. So these are all visible lasers. The first one that was developed was in the infrared region, 8500 angstrom range, reddish type of a IR type of a laser. So when you take a diode of this type, these are all special LEDs, light emitting diodes. So they are made out of third group, fifth group, second group, sixth group combinations, and these are special LEDs. When they are forward biased, because of certain interactions, the recombination of electrons or coming down of electrons to the lower level results into emission of laser light. Anything more special about these diodes? Yes. First, they are said to be direct band gap type. These are some technical words, but I'll just tell you that they are there. And they are also highly doped. So the percentage of doping level is extremely high. That makes the two regions very compact and their boundary is very thin. And thirdly, what about the size? The size of the layers could be in microns, and the overall size of the complete laser diode is about 1 millimeter in size. Forget just about additionally the electrodes, that's all. And it comes so low size, low power, it consumes very little power. So what happens is when the electrons undergo transitions, the top surface and the bottom surface is extremely polished, and that results into, and one side is partially polished. The result is those photons keep on bouncing up and down, and when they are extremely coherent and attached to each other, like all the properties of lasers that we talked of, you get a beam of laser light that shoots up. There is obviously one very important advantage of using semiconducting lasers, and that is the amount of additional circuits that are required are very little, and they work in the same range in which integrated circuits work. That means from roughly around 5 volts to about 12 volts, that's the range. That's very easily available direct current that is available at all places, batteries and so many other techniques. And that's why these semiconducting lasers consume very little power, and they can be easily generated with a very small amount of voltage, and they can be used therefore in a variety of ways. And the most common ones I talked of last time, that is reading and writing CDs, and so ROM and RAM and all that comes because of this. And all those laser pointers that we talked of are all semiconducting lasers nowadays. There are only just a couple of batteries inside and the pointer begins to work. That's how semiconducting lasers work. Which ones? As I said, you need different colors. So the one that is used for red in the actual visible range is a combination of a number of elements, and that is GaAsInP. That means gallium, arsenic, indium and phosphorus are combined in certain ratios, and you get this particular type of a semiconductor. If you use gallium and phosphorus, gallium phosphide, then you get green light. The first one was the red light. If you use gallium nitride, GaN, then you get blue type of light. So all these are different type of lasers that you tend to get. You also have some other ones. Cadmium sulfide is used sometimes, indium phosphide is used, zinc sulfide is used, and so forth. So there are different combinations that are tried out, and so many industries are trying out so many different types of semiconducting diodes. There is actually one more type of a diode that is used. So you might just come about this information, but these are known as pin diodes. Actually, PIN is what it is. P is positive, E is intrinsic, that means without any doping, and N is negative type of a semiconductor, and they are merged to form a diode, and the inner surfaces are highly polished, and it is between these two that you start getting laser beams that are produced. So these are also semiconducting diodes that are lasers. So semiconducting lasers are produced in this manner. All these are among the most common type of lasers that are produced. There is one more, and that is talked of nowadays, which is known as an excimer laser. In all many of the medical applications, this excimer laser is used. It's an interesting area. So just for your information, you must have heard of this. Actually, the word excimer is a abbreviation. It is excited dimer. Di means two. Mer is a unit that repeats itself, like polymer. So polymer is a repetition of a particular carbon based pattern that keeps on repeating. Long back we talked to this. So excimer is an unstable excited molecule made by combination of smaller molecules, and its metastable state is extremely unstable. In nanoseconds it splits up back again and emits a radiation. This radiation then triggers on others to give out their own radiation, and that becomes the laser. So you have two molecules, they split, 1, 2 and AB are the original molecules, they split. So it becomes 1, 2, A and B. Or it is possible that you could have both 1, 1 molecule and AA molecule, and they split into one separate, A separate, one separate, one separate, A separate, A separate, and then these combine to form A1. But A1 is extremely unstable. So A1 splits back and they again go back to their original level. And then what it produces is the laser. It's not as simple as I am talking of, it's a little more complex, and because the process of triggering on is done by electrical methods and so forth through discharges. What do you use? The most common type uses krypton fluoride. So you have krypton gas and fluorine gas, and the fluorine splits up and the krypton molecule splits up and they get krypton atoms and the fluorine atoms, and the krypton fluoride is formed and it cannot remain, so it breaks up and it gives out a photon, and a number of them under special conditions form a laser, and that's dimer, and that is nothing but the excimer lasers. This is a very advanced area of even understanding how it works. I have just given that to you so that I am sure I would love to have all you people reach the highest possible levels of understanding as far as frontline work and how it works. So that's the excimer lasers, and I told you where it is used. All those eye surgeries etc. use excimer lasers, femto lasers and so forth. These are all excimer lasers. That brings us to the most advanced type of lasers that are talked of today, officially talked of, and these are nothing but the ones that deal with certain optical fibers modified in a certain manner. I told you what optical fibers are. It's a central core of one refractive index, another covering with another refractive index, and it ensures that light remains within it, and that's how the light gets bent around and that becomes an optical fiber. The difference is because of the refractive index outside. So what they do in this particular case is they make the inner line still more thin and more thin and more thin and so forth, and instead of having one more layer on top, which is known as a cladding, they have two layers of cladding. Obviously, if it is going to get thinner, then the beam, the only specific ones that are going to match out are going to remain inside. Rest of them are all going to be scattered off. So you retain only one particular type of wavelength of light that is retained inside. You go one step further. You change the even inside. You make sandwiches, and these sandwiches are made with the addition of a rare earth to these, and ytterbium is the rare earth that is added to the glass that is made, and that changes the refractive index of these sandwich layers. So the tube has sandwich layers like this in between, And because of this, when the light passes through certain, it acts like a grating, and certain type of wavelengths are chopped off, and only one particular type which is exactly in matched phase and coherent and so forth is the one that is left. And that is nothing but the laser that we are talking of. And what do? You loop it around and make it pass through the same cycle again and again, and that builds up the necessary laser beam that is required. And the advantage is very simple. Since it is through an optical fiber, you can bend it around anywhere that you want, and you can put it through your body and send it to any particular area that you want. And so you have a fiber optic laser. What I have told you is the simplest form of how a fiber optic laser is made. Let me mention that the actual processes involve a lot of more scientific background behind all this and technical aspects, but this is the crux of how these different types of lasers are made. So by chance, if you start reading about them, it shouldn't happen that everything is completely blank. Oh yes, I know what this is. Oh yes, this is what it is like. You can then figure out how things work. If you liked whatever I have said, uh, please like and subscribe to this channel. If you press the bell icon, you would know what I'm going to come up with next time and so forth. Tell your friends about this. Be proud that you know a little more about lasers now, even if you're not from the science field and not from the science area. But it's fun to have a lot of good knowledge. That ends our discussion as far as light is concerned. And so we need to talk of something else. And I'm specifically thinking of two more areas. One is going back to the origin, as to how the whole universe began. We must know how things started off, and how all this, including the sun and the earth and the solar system, were produced starting right from the Big Bang. That is one area that is pretty interesting to talk on. And the second one obviously is talking of radioactivity, which is equally important. So tell me to talk and discuss about these areas. This is Prakash Zok saying goodbye. Namaskar.